Let's look at digital signatures in more detail, because this technique is used not only to authenticate where a document came from, but it can also be used to ensure data integrity. Data integrity means that the data has not been tampered with on its journey from the sender to the recipient. The sender, Mr. Blue, has a document that he wants to send to Violet. The document is not confidential, but Mr. Blue wants to ensure that Violet knows, first, that he is the one who sent the document, and second, that the document was not tampered with along the way. The first thing Mr. Blue does is create a digest of the document using a one-way cryptographic hash function. A cryptographic hash is a function that maps a message of arbitrary size to a document of some relatively small fixed size. One property of a cryptographic hash is that if you only have a digest, it is nearly impossible to construct not only the original document, but any document that has that same digest. Another property is that each message will map to a relatively unique digest. In other words, if you have two different documents, their digests will also be different. One way you will hear people state this property is that the hash function has very few collisions. Once a digest has been created, Mr. Blue encrypts the digest with his private key. The encrypted digest acts as Mr. Blue's digital signature of the message. He then sends the message, which is not encrypted, and the digest, which is encrypted, to Violet. When Violet receives the message, she decrypts the signature and obtains the original digest. She now has the digest and the original document. In order to verify that the document is from Mr. Blue and it has not been tampered with, she creates her own digest of the message using the same cryptographic hash function that Mr. Blue used. If the same cryptographic hash function is applied to the same message, the same digest will result. Therefore, she simply compares the digest she generated with the digest that she obtained from decrypting Mr. Blue's signature. The only way that the two digests can be equivalent is if 1, the signature received came from Mr. Blue, and 2, the message received was not tampered with. If the two digests do not match, Violet knows that something went wrong along the way, and she does not accept the signed document. Let's assume that a client has a public key of a web server. Since anyone on the internet can claim to be a particular web server and issue public keys, there needs to be some way to verify that a public key really is from the web server it says it is. We'll talk about how we do this in the next slide. But for now, let's assume that the public key has been verified. To establish a secure connection, the client first sends a brief message to the server. And the server signs the message and sends it back. Once the client is convinced that she really is talking to the server, she generates a symmetric key. She encrypts the symmetric key using the server's public key and sends the key to the server. The server receives the symmetric key, and from that point on, they use symmetric key cryptography to carry on their secure conversation. One thing you might wonder is why they don't just use public key cryptography for the entire secure conversation. The main reason is speed. Secret key cryptography is significantly faster than public key cryptography. Once a link has been established, there's no reason to continue using public keys. Also, keep in mind that for secure public key cryptography to work when it is used exclusively, the client would have to generate a public-private key pair so that the server could send private messages to the client. Let's talk about how a client can trust that she has the real public key of a particular server. This is accomplished by using certificates. A certificate contains the following: the public key of the server, information about the server, the name of the company that issued the certificate, and a timestamp so that the certificate will eventually expire. To be useful, a certificate must be digitally signed by a trusted certificate issuer, like VeriSign or Thought. But we still need the public keys of the certificate issuers in order to authenticate their signatures. So, why do we trust the public keys of the certificate issuers? The answer is that those public keys are widely distributed and, in fact, are built into our browsers. Since certificates can be digitally signed by a trusted certificate issuer, websites make their certificates publicly available instead of their public keys. There's one more topic that needs to be addressed to complete the discussion on how SSL and TLS work: data integrity. Even if data is encrypted, some malicious person could still intercept the data and modify it or deliver only a portion of it. So even if the data could not be read, receivers could potentially receive data they thought was correct but was not. To make sure the receiver knows when there is a problem, a message authentication code, or MAC, is used. A MAC is similar to a digital signature in the way that it works, but instead of the digest being encrypted with a private key, it's encrypted with the symmetric key that both parties are using. This is faster than encrypting with the private key, and it's usually sufficient. It does have a downside. Unlike digital signatures, where the digest is encrypted with a private key, MACs do not provide the property of non-repudiation. That means that we can't necessarily prove that the sender sent a particular message. The receiver also has a copy of the key that is being used to, quote, sign a given message. So the sender can always claim that the receiver was the one who sent the message. In effect, that the receiver forged the message. Now let's put everything together. This client wants to set up a secure connection with Amazon. The client's browser already contains a public key for the certificate authority that Amazon uses. Amazon has its private key. First, the client sends a request to Amazon. Then, Amazon sends its certificate to the client. Remember that the certificate contains Amazon's public key, and the certificate is signed by a certificate authority whose public key is already built in to the client's web browser. So the client saves Amazon's public key. Then the client sends a message to Amazon for Amazon to sign. Amazon signs it and sends it back. At this point, trust has been established, so the client generates a symmetric key, and it sends the symmetric key to Amazon. Amazon stores the symmetric key, and finally, a secure conversation using symmetric key encryption and message authentication codes can begin. And that is an overview of how SSL and TLS works. I hope you enjoyed this brief video, and I'll see you in the next one.